So, hello everyone, my name is Oz and I am at the Lawrence Berkeley National Lab. And today I will be talking about a popular sparse matrix operation and its performance aspects on recent and emerging HPC systems with accelerators. So the matrix multiplication is rather more of a challenging operation. It is among one of the most studied operations in the literature. There is a sparse kernels, there are the dust kernels. We call a kernel sparse if at least one of the matrices involved in the multiplication is sparse. So there are several variants as you see here. We can multiply a sparse matrix with a dense vector or another sparse matrix or a sparse vector or a dense matrix. These kernels still attract attention due to the challenges associated with them. Best practices for these kernels widely differ because each has its own unique set of features. For example, if you have an optimization technique that works well for a kernel that runs sequentially, when you try to port this to a shared memory architecture or onto GPUs, it might not work very well because it has a lot of synchronization overlaps. So each has its own unique set of features, and one must focus on one thing to get better performance. In this talk, I will be focusing on tall and skinny dense matrix multiplication. So we are going to call this SpMM. This operation has traditional application area in scientific computing being used in Bulk iterative solvers or factorization, the matrix factorization. It has also attracted attention recently in machine learning, occurring in graph neural networks or sparse deep neural networks. So why do we need another study on this operation now? So there are two reasons. Again, as I said, first, it has been made popular by some deep learning frameworks. And second, the GPUs are here to stay and spread. So more and more HPC systems will be built with these GPUs. So this is the trend. And our goal is to study some of the design choices on distributed memory HPC environments that contain GPUs for this operation. We will look into design issues such as data decomposition, parallel algorithms, communication semantics, how to orchestrate the communication, and some local computation aspects. There are things I will not go into, such as different storage formats for the sparse matrices. So we would like to find answers to some of the questions listed here. So what is the role of the local computation and arithmetic intensity? Is it as important as when we perform this on CPUs or when we perform this on GPUs? And the importance of communication and how to best orchestrate it. We are also going to look into some of the aspects of decomposition techniques and parallel algorithms. And then we will study some performance bottlenecks and how to best overcome them. As you will see, answers to these questions are going to be largely different for HPC systems with GPUs. So we have the SpMM of the form C is equal to A times B. We have a sparse matrix A, which is going to be assumed to be square. And we have the dense matrices B and C. As for decomposition, we are going to assume that the sparse matrix is 2D partition, which results in better load balance because it's not true for dense matrices. So we investigate both one-dimensional and two-dimensional partitioning of the dense matrices. We have P processes and we assume a square process grid. As for the parallel algorithms, it is going to depend on which matrix is stationary. One of the three matrices in this multiplication can be stationary, can be the sparse matrix or one of the dense matrices. And according to this, it's going to get its name from according to which matrix is stationary. As for the decomposition, when we have one decomposition of the dense matrices, we are going to have replication. And when we have replication, we are going to have an algorithm that is almost like a 1.5D algorithm. So we are going to call it 1.5D. Here, this table shows all of the combinations of these decompositions and parallel algorithms, and which we are going to investigate and not. We will not go into the details of the B stationary algorithm because they have the same computational and communication complexity with the C stationary algorithms when the sparse matrix is to car. So this is the case in this talk. We also don't investigate the 1.5D C stationary algorithm. This is because this algorithm necessitates the communication or replication of the entire sparse matrix or the entire dense matrix, which is not feasible. In the stationary algorithms, the sparse matrix stays in place, and we communicate the dense matrices or replicate or communicate the dense matrices. Here we have two variants. If the dense matrices are partitioned in 1D, we have 1.5D A stationary SpMM, and if they are partitioned in 2D, we have a 2D A stationary SpMM. So here are two A stationary algorithms. Here in these figures, the blue submatrices present the view of a process, and the gray submatrices present which submatrices are replicated or communicated. As you can see here, both algorithms have similar structure. They first replicate the input dense matrix, and then they perform some computation, and then they accumulate the output dense matrix. The difference here is that 1.5D algorithm performs this process in a single stage, whereas the 2D algorithm performs this process in multiple stages. To be exact, this number of stages here is square root of P. In the C stationary algorithms, the output dense matrix stays in place, and we communicate the sparse matrix and the input dense matrix. Here again, we have two variants according to the decomposition of the dense matrices. We are not going to talk about the 1D partition of dense matrices because this requires a lot of communication. And in the 2D partitioned dense matrices case, the algorithm works by first replicating the sparse matrix across the row of the process grid, and then it replicates the input dense matrix across the columns of the process grid, and then it replicates, it performs a local multiplication. So we have these decomposition techniques, we have these algorithms. How do we approach to implement these? We have two approaches. First is the bulk-synchronous approach with MPI collectives, and the second is the asynchronous approach with the RDMAs. In the bulk-synchronous approach, we use COMBLAS for storing and performing operation on sparse matrices. In the asynchronous one, we use Berkeley container library. In the bulk-synchronous approach, the CPUs are used to coordinate communication. And in the asynchronous one, we use SpMM to realize the RDMAs. In both, the local multiplications are performed with NVIDIA's CUDA-Sparse library. In the bulk-synchronous approach, the submatrices originally stay on host memory, and they are copied back and forth between host and the device memory. In the asynchronous approach, the submatrices stay on device, and they are directly communicated between devices on different nodes. This latter option, this asynchronous option, is arguably faster, but we include both options because not all MPI vendors or architectures may have support for this type of RDMA. For the bulk synchronous approaches, we rely on MPI collectors. We have stuff like all-gather, reduce, scatter, all these collective operations. The communication is explicitly coordinated by the CPU resources. And an example execution flow is the matrices usually stay on the host memory. And whenever we need some local computation to do, we ask the GPU to perform the computation. And after this computation is complete, we collect the result and put the result on host memory again. If we compare the bulk synchronous approaches in terms of their communication aspects, they differ in two directions. In the first one, they differ in which matrices they communicate. The A stationary algorithms communicate the dense matrices, whereas the C stationary algorithms communicate one sparse and one dense matrix. And in terms of communication costs, the 2D algorithms have an extra factor in both the latency and the bandwidth components of the communication cost. In terms of memory footprint, the 1.5D algorithms have higher memory footprint than the 2D algorithms. And finally, in terms of local handling of the local computation, all of the algorithms have the same overall computation complexity, local computation complexity. But the difference is that the 1.5D algorithms do not split this computation, while the 2D algorithms do so. For the asynchronous approaches, we rely on RDMAs. So each process here performs remote get and put requests, which are directly executed by the network interface card. These are one-sided operations. There are two ways to realize this. One is through the NVIDIA's SpMM library, and second is the CUDA-aware MPI. In our work, we will be using the NVIDIA's SpMM implementation. So there are some obvious advantages to the asynchronous approach. The obvious one is there's no synchronization needed. This is more likely to result in better load balance. It also utilizes the remote RDMAs, so it can bypass the CPU and the host memory, which can prove quite costly. There are also a couple of optimizations we apply here. The first is the iteration offset. So this is to reduce the loss on the network interface cards by ensuring that the processes make their put and get requests to different network interface cards. And we also have remote prefetching, where we prefetch the submatrices or the tiles of the upcoming iterations. And this enables overlapping of computation and communication. Here we consider a wide variety of sparse matrix inputs. These represent the problems from graph neural networks, matrix factorization, eigensolver problems, or some problem in bioinformatics. We try out both balanced and imbalanced instances. In our evaluations, we test 5 algorithms. 3 of them are bulk-synchronous and 2 of them are asynchronous. Here, this table shows here which flavor is runs which algorithm. And we conduct our experiments on IBM Summit system at OLCF. So each node in this system has 2 circuits, and they are equipped with 2 PowerPC 9 CPUs and 6 NVIDIA Volta GPUs. Each GPU has 16 GB of memory, and finally we use 6 processes per node, 1 for each GPU. Here the CPUs are not utilized for computation, and they are only responsible in the bulk-synchronous algorithms for orchestrating communication. We have an abbreviation that consists of 3 parts. In the first part, we name the parallel algorithm, whether it is A stationary or C stationary. If it is A stationary, it's going to be regarded as SA, and if it is C stationary, it's going to be abbreviated with CC. And then we have the decomposition technique, 1.5D or 2D, and then we have the communication orchestration method, which can be asynchronous AS or bulk-synchronous BS. Here in these experiments, we show the total time spent in local multiplication calls, with varying it with the number of partitions as the number of partitions increases. The goal of these experiments is to see what happens when we try to strong scale the sparse kernels on distributed memory machines with GPUs. Here we perform the same amount of computations by splitting into a number of partitions, which are here varied in the x-axis. It is expected that the local computations will start achieve a smaller percentage of the peak performance as we increase the number of partitions. But we want to know to which extent this affects this is affected by the decomposition techniques. As you can see here, the 2D algorithms spend more and more time on local SpMM computations. This makes it not strongly scalable, even if there were no communication costs or no other costs. The 1.5D algorithm, on the other hand, exhibits better scalability. And these figures also show that if you want to scale parallel SpMM, we should better hide local multiplication overhead or rely on an algorithm that does not split computation a lot. Next, we compare CPU MPI and CUDA-aware MPI and its effect on the decomposition schemes. So here we benchmark CPU and GPU orchestrated communication. We isolate the performance of communication primitives by executing collective operations that are typically found in the 1.5D and the 2D algorithms. Here, the left plots show the 1.5D algorithms, decompositions, and the right plots show the 2D decompositions. Here, row refers to the MPI collectives performed on the row dimension of the process grid, such as reduce scatter, and the call refers to the collectives performed on the column dimension of the process grid. An example here is altogether, and total means that both of them are performed in the simultaneously. These figures show that the 2D algorithms take better advantage of the available bandwidth, and the CUDA-aware MPI seem to be not using the GPU direct RDMA, as these are significantly worse than the bandwidth sustained by the CPU orchestrated communication. So this may be due to the collective implementations of the underlying MPI implementation, not taking advantage of the RDMAs yet. Next, we look into the performance of the 5 algorithms compared. The bulk-synchronous, 2 of them were bulk-synchronous, and the asynchronous, 2 of them were asynchronous algorithms. Here, these plots, all 6 of them, show that the asynchronous scheme achieve better parallel runtime than the bulk-synchronous scheme in almost all test instances. So their better performance can be attributed to 2 contributing factors related to both communication and computation. First, the asynchronous approaches orchestrate the communication more efficiently by relying on RDMAs, and they spread the possible communication imbalance across multiple stages in which one can hide these communication overlaps by overlapping with local multiplies. Remember that we had stuff like prefetching, so there are a lot of opportunity to overlap communication and computation. Among the compared schemes for the bulk-synchronous approaches, the 1.5D astationary algorithm exhibits superior scalability. So this is for the bulk-synchronous approaches. The replication here seems to be paying off if it is able to better make use of GPU resources. There's one drawback, however. This algorithm has an increased memory footprint, and it has the possibility of running out of memory at small node counts. And as you can see here, there are some plots where it has some missing points due to out of memory error. Finally, we focus on the performance of the bulk-synchronous schemes. So among the 3 bulk-synchronous algorithms, it can be said that the 2D astationary algorithm usually constitutes a smaller portion of the overall execution time compared to the 2 other. And we see that the 1.5D algorithm, the astationary 1.5D algorithm is more scalable. There are 2 main reasons for that. Because this is mainly because it does not suffer from load imbalance as much as the other bulk-synchronous approaches do. This is because it does not perform split the computations in stages. And secondly, it does not communication sparse matrix. Here, the instance NM8 is an imbalance matrix, and you can see that it does not suffer as much as the other algorithms do of sparse matrix being imbalanced. So if we conclude, we saw that the arithmetic intensity plays a more crucial role in the performance of parallel SpMM. than running on GPUs than on CPUs. So the higher arithmetic intensity of 1.5D algorithms in local multiplication enables them to scale better than the 2D algorithms. And the 1.5D algorithms often exhibit better scalability. And when we compare the asynchronous and the bulk-synchronous approaches, the higher performance of the asynchronous implementation can be attributed to their lower communication overhead due to using RDMAs and their better ability to hide the load imbalances in both the communication and the computation. And finally, regarding the 2D bulk-synchronous algorithms, the A-stationary algorithms are more preferable to the C-stationary or B-stationary algorithms when the sparse matrix is highly load imbalanced. This concludes my talk. Thank you for your attention. And if you have any questions, I would like to answer them.